ॐ भूर्भुवस्वः तत्सवितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो नः प्रचोदयात्.
Okay, so today we start a new programming language, which is Java. As you all know, Java is one of the most popular object-oriented languages in the world, and Java has become a de facto language in many domains, whether it is gaming applications, whether it's healthcare applications, whether it's telecom applications. Java has gained a lot of support. Today there are millions of programmers who know Java. There are millions of systems in which Java is getting used, and the juggernaut of Java seems to be going growing in a very robust manner, and I am sure for the next 10 years at least there won't be too many variations in this change. The other point is that Java is evolving. Java as we knew it 5 years back or 10 years back is a lot different from the Java as we know it today. There has been a continuous effort to upgrade this language, and perhaps that's the reason why it has been so successful and so strong. What we are going to do today is basically take you through some of the features of Java, some of the unique features of Java, talk a little about the different versions of Java, and then we will look at how to create an application on Java on the cloud, and basically that is where we'll conclude today's session. So let us look at some of the unique features of Java, but before that a little bit about the history of Java. Java was created somewhere around 1995-96. Interestingly, the story of Java is that it was not really created as a web programming language or as a general purpose programming language. It was meant to be created as an embedded programming language which was supposed to run on small embedded devices like refrigerators, like electronic devices and all that. Its original name was Oak, O-A-K, and basically it was later renamed as Java. So Java has certain very interesting features in terms of its virtual machine utilization. It's one of the first languages which has used the virtual machine concept remarkably well. So we will talk a little bit about that also today. In addition, we will also see what are the various avatars of Java. We have Java today very popular on mobile phones. We'll talk a little bit about that. Java is used in creating interesting games and applets and browser-based applications. Java has found its right place actually, or its major deployment at the back end, at the server side. So we'll talk a little bit about those, and we'll also see how to create small Java programs. So historically speaking, Java was created in 1995. It was called Oak, and to summarize, it was not created as a web programming language. It was essentially created as a language which would enable embedded device applications, a language which would run on its own virtual machine on an operating system, and basically would flourish there. And then the internet happened, and we know the rest of it is history, because now there is hardly any internet-based programmer who doesn't use Java. There's hardly any of those. There are close cousins of Java like the C#, like many other languages, which have borrowed a lot of programming habits from, or programming concepts from Java, and successfully defined some better forms or some better variations of that language. So let's start with what makes Java so unique and so different. So let's look at some of the salient features of Java, and then travel forward. Next. Okay. Now, some of these things may make sense right away. Some of them actually may not make sense to you straight. But let's even then just talk about it, and some of those features will become more clear as we progress through this course. One of the things they talk about is Java is web enabled and network savvy. Let me first talk about this thing in the right order. Basically, what the first thing which stands out to a programmer is Java is very secure, which means that there are two things which Java has which ensure that Java is a secure programming language. This feature is mainly addressed towards C and C++ programmers who believe that the C and C++ compilers are pretty weak and they really don't catch half the things which the programmer makes mistakes with. So a common thing is the way arrays are handled in C. If I have a C program and I say int a10, that means actually I'm declaring an array of 10 elements in C, and I say let's say 10. Actually, you know, in C, the element index is from 0 to 9, and I say A10 or A11 is equal to 25. Chances are that this program may run, and at the time of execution may actually, sometimes it will execute also and give you a proper success with this line. Sometimes it may give you a segmentation fault or that kind of error. Meaning, when this line gets executed, there is no array bound checking in C. So what it means is that here I may get away with the execution. The C program may actually execute this line A10 is equal to 25 because the runtime system of C really doesn't bother to check whether the array index has exceeded the value. For those of you, again, it is A10 means the index is 0 to 9. So A10 actually exceeds the index. By the same token, it is possible that A11 is equal to 35 may also execute sometimes in C. There is no protection. If at all, the protection has to be there. It has to be forced by the programmer. That is, the programmer, before he uses a subscript, let's say I, he has to check whether the subscript is within this range or not, and then only allow this thing to happen. So the onus of checking whether the subscript is in the right range or not is with the C programmer, and as expected, sometimes it will give unexpected behavior. Now, that's the first thing which we get through in C, in Java, that array bounds are never violated. So in Java, one can guarantee that this line or this line will always give an exception, which is famously called the array index out of bounds exception. This line will never be accepted in a Java system. When you run this program in Java, invariably it will give an array index out of bounds exception. So it is guarded. So it is no way that this line will ever execute. Please remember that this kind of code is used by hackers to get into the operating system by exceeding the size of the allocated array. This is a common strategy used to get into the kernel and see if you can disrupt the kernel. This is absolutely not permitted. So that's why we say Java is secure. One of the reasons why you say Java is secure. Now, in C or in C++, we often use pointers, and then we can get address of different data structures. So you can say, for example, int star p, and then you could say, that means I'm declaring p as a pointer to an integer, and then I can say, like, let's say there is an array A of 10 elements. So I can say p is equal to ampersand A4. That is, I am getting the address of the fifth element into p, and then if I say printf, percentage d or x p, then I am going to get the address of the fifth element of A. That means there is possibility of address manipulation, address access, and if I want to know the address of this element, of course in virtual memory space, I can still find that out. Now, while this might seem like a very exciting feature for low-level programming, and it might seem like a good feature to have when you're doing device drivers and all. In the hands of application programmer, it is not really a very it is a powerful feature, but it is not really a very useful feature, because what happens is certain application programmers may tend to misuse or incorrectly use the address manipulation. So what has happened over time is the people who have created Java realized that while address manipulation was giving a lot of power to the C++ programmers when they were writing device drivers, in general purpose application programs, address modification, address manipulation, which C provided in a very nice manner, was not required. Actually, it was creating more confusion in the minds of the programmer. Manipulation, instead of benefiting us, is causing us more confusion. So one of the things which the Java guys have decided is there are no pointers, so there is no possibility of address manipulation in Java at all. You cannot have the address of a variable. You can't ask for the address of the fifth element, fourth element. There's no address. So that is one of the reasons why they say Java is more safe, because you can't again go into different territories, go into some area which you are not supposed to, because potentially I can do something like this. I can say p, because it's an integer pointer, I can say p is equal to maybe 0x 3453, and then say star p is equal to 50. So basically what I'm trying to do here is I'm trying to manipulate this physical address 3453. Sorry, it's not a physical address in most systems, it's a virtual address, but it opens up an ability to attack that area. Now that area may be somewhere in the kernel, or that area may be in some reserved space, or it may expect very uncertain results. So I'm able to do this kind of thing in C or C++. This is not at all allowed in Java. So that makes in many ways the language secure. So we have looked at arrays, and we have looked at pointers or the absence of pointers as some of the key features the Java language brings to the table. Now Java compilers are very strong compilers, and let me make that point. So the enforcement of types is very stringent. Now we'll discuss this in detail. We'll look at different examples of making this happen, all of that. But let's at the first level understand what it means. Okay, so let's say I have int I equal to 10, and I have, let's say, a float f. Now a C compiler will not crypt too much if we say f is is 0.7, and a C compiler, if we say I is equal to f, the C compiler will not worry too much. It will compile this program, and what it will happen is, because f is a float and I is an integer, the float will be truncated, and if I say at this stage printf of I will get 0. The reason I'll get 0 is because f, being a float, cannot fit into an integer. Integer doesn't have the capability of holding a decimal part. Technically floats are much bigger than ints in their storage and in their storage capabilities. So when I say f is equal to I is equal to f, this is actually called in many languages as narrowing. This is called narrowing. What is narrowing? A big fat data type trying to get into a small variable type. I is a smaller and f is bigger, so a fat guy is trying to enter a small guy, and as a result this is called narrowing. Now the point we are making is, because there is no strong type checking in C or also in many C++ versions, this line will be allowed by the compiler without any warning, without any issue, or some compilers may just give a warning but still go ahead and compile. And that is what we mean by there is no type enforcement which happens in C, or for that matter in most C++ compilers. And this results into problem, because the programmer may have something else in mind. He actually didn't realize that the fractional part will get truncated at this point. So what if I were to write a similar line in Java? The Java compiler would immediately shout on this line. He would say, there's absolutely no way in this form we are going to allow this statement, because he'll say narrowing errors are going to be caught automatically by the Java compiler, which the C++ compilers don't catch. So this leads to strong type enforcement. Now this is not the complete story. The complete story will reveal itself as we travel deeper into Java and understand more things about Java. Let's now go forward and understand a little bit more about the other features which are listed here. Let's also talk about what is this web aspect of Java, and well, we'll come back to this feature of web can deliver software, no more installation or updates, just a bookmark. We'll talk about it in this lecture, but a little while later, as to what do we mean by web can deliver a software. Okay, so the other advantages, if we can move down, the other advantages are, well, Java has a lot of good things, and we are not listing all of the good things. And one of the things which we forgot to list is obviously Java is object oriented, which we'll talk at length about that. So Java's client server library is easy to use, and he puts in a very nice line: ordinary mortals can do network programming. That's a very nice way of doing it. Again, it is addressing C and C++ people, where network programming used to be a very deep science. People had to struggle as if it was a rocket science to do network programming in C or in C++. The creation of sockets, the creation of TCP sockets, the creation of datagram sockets, the creation of multi-threading, and then sending a packet from process A to process B, and then receiving it in a different kind of thread. It used to be so arcane and so esoteric in programmers in C and C++ that in interviews people used to be asked, oh, you know C? Oh, have you done any network programming? As if that was a litmus test of the proficiency with the C language. And so also in many aspects of C, simple database calls were very difficult to make in C. If you had to make a SQL request to a database through C, you had to use versions like ProC or Open Client, APIs, and because of the pointers and all, the code used to become so messy that you required a substantial degree of expertise to do with C. Having said that, while Java has made a lot of these libraries and functionality very easy to use, and so to say democratize the usage of databases, of object-oriented technology, of client-server technology, I'm not saying for a moment that C doesn't bring a lot of power also. The only thing is C is perceived as difficult to use for doing client-server programming, for 3D graphics, for JDBC kind of programming. That is where Java scores. But of course, there are certain areas in telecom and device drivers and systems programming where you can't just do without C. I can't imagine writing a DSP algorithm in Java. Such things need to be written in C. I mean, we have to give due respects to languages like C and C++, as we say that Java does make a lot of these network programming and database programming very easy to handle, or for that matter, distributed programming. Anybody would agree that writing an RMI program, RMI stands for Remote Method Invocation, which is an object-oriented version of those of you who know in C, there is something called Remote Procedure Call. The Remote Procedure Call is for distributed computing in C language. Understanding RPC programming, lot more difficult than RMI, lot more. So let's travel to the next slide to see something else about Java. Next. Okay. So here we are depicting some nice applications which are created in Java. There has always been a discussion on Java that Java, while good at the functionality, multi-threading, object orientation and all that, its user interface is not so exciting. While that is true for a large extent, when you write Java programming, Java user interface programming has come using two types of toolkits. One is called the abstract window toolkit. The quality of the user interface continues to be not very good, but some work has been done with Swing, which is a more modern avatar of AWT, which is a lot easier to program than AWTs, and lot more, the quality of the user interface is much better. But if you compare Swing with today's requirements of the web, like the rich internet applications, we have languages like Flex and all that kind of stuff. I think Java still has a lot to learn from the Flex-based programming, Flash-based programming of Adobe. And on that, I think while the user interface we are having here, we are depicting a Hubble Space Telescope monitoring, showing the management of a telescope through Java. While all that is possible through client-server programming, through distributed programming, I think Java gives an immense power when it comes to client-server, when it comes to distributed database. But the quality of user interface, I will have my opinion reserved, because I am sure Java is not the best language when it comes to good quality UI. I mean, Swing is a lot better than AWT, but I wouldn't lay my bets on it. Next. You will see some more of these nice user interfaces, but I'm sure while we can do all of this in Java, I'm sure those of you who have a little more background on Flex and Flash and all that, I'm sure this is nothing great as far as UI programming is concerned. So let's quickly move over to the next slide. Yeah, let's hold it here, and I shall use the whiteboard to elaborate a little more about this Java being cross-platform and all that kind of stuff. Okay. Before we go on to Java, the common situation is that of a C compiler. So in C, what happens? You start with a program. Let's say hello.c. Then what do? You take this program, write it, and you give it to a C compiler. The C compiler could be GCC if you're working on a Linux system. It could be CL if you're working on a Microsoft system, or it could be Turbo C if you're working with the Borland suite of products. And what does this do? It produces, during the compilation there is a automatic linking. In fact, CL stands for compile and link. So I'm not going to go through the linking phase, but we get something like the hello.exe file. Now, here is where lies the rub, is the fact that I have hello.c, which has been transformed into hello.exe. Now you will say, yeah, most languages work that way. Now the problem is the hello.exe will work on the environment on which it is compiled. The point I'm making is that if hello.exe was created through the GCC compiler available on Linux, then the hello.exe, or as we say the a.out, if you are working on a Linux system, it could be named anything else, but it would be essentially in the a.out format. This would work only on the Linux system. The point I'm making is, if you get hello.c and compile it with the GCC compiler, you get some a.out, you get some name, that executable is going to work only on the Linux system on which it is creating. Further, it will work on the Linux system if it is put on an Intel hardware. I mean, it was compiled on an Intel hardware. It will work only on the Intel platform on which it was compiled. It will work on other machines as long as they are compatible in the Intel platform and compatible in the operating system on which the program was originally compiled. Which means that this exe, or if you will, the a.out, which I have created on a Linux system, if I take it to a Windows box and say, hey Mr. a.out, execute yourself on the Windows XP or Windows Vista or whatever, the a.out simply will not be recognized by the Windows runtime system, because they will say, because this a.out has been built to run on an Intel Linux system and it is not running on an Intel Windows system. The processor may be the same, but it is not just dependent on the processor, it's also dependent on the operating system. So what does this mean? It means that if I am developing a program which needs to run on the 52 different versions of Linux, and let's say on Windows and on Macintosh, the program simply has to be compiled 54 number of times, 52 plus Mac plus Windows. Unless I am going to compile this program 54 number of times and test it on 54 different hardware and obviously operating system software, this program is not going to be portable in its executable form on different platforms. So what I need to do, if I have a Linux box and I have a Windows box, I'll have to take the same hello.c. See, this hello.c may be taken as the same hello.c for Linux, but even there might be issue. But those are separate issues. Those are called source code compatibility issues. Today, with the coming of POSIX and all that, we may not have to change this hello.c quite a lot, or maybe not at all, if you want to create a hello.c for the Windows system. So this hello.c, which is created for the Linux system, the same hello.c you could take at the source code form and then pass it through the CL compiler, which will give you a hello.exe, which will run on a Windows XP. So to clear the air, hello.c, I take it. If I am on a Linux system, I give it to a GCC compiler. It will compile it. I'll get an a.out file which I want to call. I can call it hello.exe, but that just won't run on any other operating system other than a Linux Intel operating system. If I want to make executable on the Windows operating system, then I need to take the hello.c, give it to a CL. CL is the compiler and linker for Microsoft, and then create it in hello.exe. It will run on the Windows platform. Can the same hello.exe run on this Linux platform? No, absolutely not. I have to get the a.out format to run on Linux. So basically, our programs are incapable of moving cross-platform. A machine, so a program which is created, which is compiled into an exe or an a.out will run for that operating system, that hardware. It will not run on any other operating system or hardware. So that creates for software developers a big nuisance, because we need to then maintain so many different variations of our application, of our program. I'm sure it's just not maintaining the variations, it's whenever you give a new version of that program, you'll have to test it out on so many different operating systems. You'll have to test it, verify it, and keep this whole process going whenever you release a new version of the product. It's very expensive from a cost perspective, it's very expensive from a resource perspective. So obviously that is where Java brings something very interesting to the table. Now let's talk about what Java does. This was a C program, so we described that a C program which is compiled into an executable on one platform doesn't move to the other platform as it is. We have to recompile it and build it onto the other platform if we have to execute it. So let's see how Java does this a little differently. And there is where we will talk about a little bit about the bytecode and the virtual machine. But let's set the ball rolling here. So if I am going to do a Java programming, and let's say I am having these two operating systems, Windows XP and Linux, both may be running on Intel. I am not really worried. I am also not really worried which version of Linux is running, whether it's the Ubuntu, whether it's the Fedora, or whether it's the Red Hat. I'm really not concerned at this stage, because that's not specific, that's not necessary for my problem definition. So I have Windows XP, I have Linux, and then what do I have? I have my program hello.java, which is running on which I have written. Now we are not going to get into hello.java right away, but there is another important thing we need to understand is, for executing Java programs, you basically need, on any platform where Java has to execute, you need a virtual machine, VM as we call it. We need a virtual machine on the Windows platform. We need a virtual machine on the Linux platform. If you don't have the virtual machine, you cannot execute Java programs. Where do you get these virtual machines? Well, today most operating systems that I know of, in fact almost all operating systems that I know of, come with a built-in Java virtual machine. If it is not available, it can be downloaded and installed on your operating system, a virtual machine. Today there is virtual machine available for any operating system, so you can install it. That is a prerequisite for running it. Is the virtual machine code same for Linux and Windows? No, it is not. And we'll soon appreciate the difference why it is not. It is called a Java virtual machine, and it is residing on Windows XP and on Linux. Now what do I do? Well, I, as usual, give it to a compiler. I have a hello.java file. I give it to a compiler. The compiler in Java is called javac. And what do I produce? I produce hello.class. So I get a class file produced. And once I have hello.class, this is normally called bytecode. Please understand that this is not executable. This is called bytecode. It's called Java bytecode. Okay. Now what is a bytecode? It's a bunch of instructions, but it's a bunch of instructions which execute not directly on Windows XP or directly on Linux, but is a bytecode which can execute only on a virtual machine. So the bytecode is like an instruction, but is like a bunch of instructions, and it is a bunch of instructions. These instructions have to be executed on a virtual machine. So basically the compilation process here, if you ask me, is this bytecode executable by itself? That means if I just take an operating system like another Linux box and try to execute this hello.class on that Linux machine as it is, it will not execute. So if I go to a Linux prompt, let's say $, and say hello, it just is not going to execute. It's going to say, I don't understand this format, because it is not a directly executable code. This is a lot different from the a.out, which is produced by C compiler, because the hello.class, which is produced by the Java compiler, is built to be understood by a virtual machine. So what happens now is that it's not going to run like this. But if I take this bytecode, which is the .class file, which is called the bytecode, and give it to a Windows XP and say Java, and say hello. Now please understand the difference. While compiling, I say javac hello.java, and I get a bytecode which is not going to run directly on an operating system. But if I say Java hello, what does it do? Well, what it does is Java calls the virtual machine. Java says, Mr. Virtual Machine, if you are available, and I'm assuming he's available, here is a bytecode hello, which I want you to get to execute. So Java is the invocation of the virtual machine. Hello is the bytecode which the virtual machine needs to execute. So what does the virtual machine do? It goes through the .class file, takes instruction by instruction, and starts executing those instructions on the Windows XP. So VM is acting like a translator. It is taking the bytecode which has been produced by the Java compiler and converting it into the machine code of Windows XP. In this case, if I say Java hello on the Linux box, where I have transported my hello.class, what happens? The Linux box also, the virtual machine on the Linux box also starts converting the hello.class to the machine code of a Linux. Now, you will understand, and some of you would have grasped this point, that there is two levels of translation. During compilation, the bytecode is becoming, the .java file is becoming bytecode. That happens during compilation, and all the testing and verification is happening, but the execution is not happening. The execution is happening when you say Java. Java is the call to the virtual machine. If the virtual machine isn't there, you can't say Java, because Java expects that the virtual machine is loaded onto your machine and available. And when you say Java hello, that time the second translation happens, that is from the intermediate form, which is the bytecode form, into the machine form, and it executes. Some of you will argue that because there is a translation during execution from an intermediate form into a machine instruction form, a lot of the time the virtual machine acts as an interpreter. So we call it, instead of using the word translator, we call it's a interpreter. Well, to be very simple, it's a correct word to use at that point, because it's really interpreting this bytecode into the machine code instruction by instruction. So will it be slow? Well, yes, it will be slow. Some people argue that Java runs 10 times as slow in certain cases as a C program, but today, with the enormous speed available at our disposal, it really is not a big issue. There have been a lot of optimizations which have happened on the virtual machine, like a JIT compiler or a JIT interpreter. JIT interpreter stands for just-in-time interpreter. There have been a lot of alterations, a lot of modifications in the virtual machine, a lot of optimizations that will make the Java program work faster. But however, it will still remain to be said that Java will run slower because of this interpretation. We will at some stage talk about the hotspot virtual machine, which has done a lot of implementations, a lot of interpretations, a lot of other things, and understand how this all happens. But this is the way a Java program works. What does it get in return? It gets immense portability. Now you see what happens. If the bytecode is tested on one platform, that is, let's say Windows XP platform, I am guaranteed almost that it's going to work on a Linux platform too. Why? Because the bytecode, if it has been tested on Windows XP and it's working fine, that means there is nothing wrong with the bytecode. If at all there is something wrong, it is wrong in the virtual machine. But you remember, virtual machines have been tested n number of times and then they are released. So we can assume that the virtual machines are pretty stable. So if I test this bytecode on its execution with this virtual machine, this bytecode is deemed as tested. I don't have to test it on different operating systems because they are not different EXEs that I am talking about. If this Java bytecode works with that virtual machine, this bytecode will more or less work with this virtual machine also. So there won't be too much of testing. And as far as I am concerned, my role ends here. When I have tested the bytecode once, when I have worked with the bytecode once, I don't really care what my customer has in terms of the operating systems. As long as, let's say there are 50 different operating systems here. As long as they have a well-tested, well-proven virtual machine, my investment is only in terms of producing the bytecode, testing it once, and testing it once on one virtual machine. And Java guarantees that if the virtual machines are correct and compatible with the Java releases, then basically that virtual machine should execute my program and produce the repeatable results as in this case. That is a guarantee given by the virtual machine as long as I'm sticking to the right version. So that makes portability and the life of an application much more easier than what we would have in case of C or C++ program. Yeah, there is another very important feature of Java. We talked about the portability. Now we'll just talk about one small feature and stop. And I'll have a lot to talk about this feature. There are no memory leaks in Java. Now why? Well, in order to do that, let's understand that I'm writing a C program. Okay? So in C program, what do? I say char star fp or cp. I'm declaring cp as a character pointer. Then I say I want some memory. I want some dynamic memory. You know, we can get static memory by declaring an array of a certain size, but sometimes in some applications I won't want to do that. I would like to go for dynamic memory. So if I want dynamic memory, all of us know in C that we use something called malloc. We say malloc 4000. What am I doing by this? I'm asking for 4000 bytes from the runtime system to be allocated to me, and C points to that. Then I start using CP here. Very many programmers, especially at the beginning stages of their C programming, have this habit that they have taken the memory, but they forget to say free on this CP. They forget to do this because of maybe getting lost in the logic, because of maybe they just didn't have the sense to do that. I'm not getting into why they didn't do this free CP, which deallocates the memory back to the runtime system. If they don't do that, this program has what is called as a classic memory leak. You're taking memory, not giving back memory. Over time, what's going to happen is this program or this system on which this program is running is going to run short of dynamic memory and the system is going to crash. Now, if you were to do this in C or C++, you would get a memory leak. The way to avoid this is in Java, they say whenever you want memory, you ask for it, but Java runtime system or the Java virtual machine will detect when that memory is not used and reclaim the memory. So to say, what it means is, in simple words, in C, the programmer is responsible for getting memory allocated and getting memory deallocated. If he doesn't do the deallocation, he causes a memory leak or a memory bleed. In Java, you get memory on demand, but it is not your responsibility. That is the programmer's responsibility to give up that memory. It is the Java virtual machine which has something called garbage collector, which actually detects which memory is not getting used and reclaims that memory. So which makes the life of Java programmer easier because he doesn't have to release memory. And there are no memory bleeds, so to say, in Java, which makes your programs little more robust and strong, because this is one of the weakness of C and C++ programming, that it's on your burden that you have to release memory. So that is taken away in Java because the Java virtual machine is watching which memory is not getting used and acquiring that memory or garbage collecting that memory. So that burden on the programmer or that discipline which is expected from a C programmer is not expected of a Java programmer. So that is a big saving in Java. And we'll talk about this at length a little later. Thanks.